Okay, so right now we are going to go ahead and talk about probability. And so what I did was I put a screen capture of what the probability section of your formula sheet looks like for Math SL. For Math Studies, your formula looks almost the same. The only difference is that yours says this for this one. And so that's what yours says, okay? But almost this exact same thing. In this conditional probability one, yours is just rearranged from this. So anyway, this is what your formula sheet looks like. In order to understand your formula sheet, you have to be able to understand the notation. And so just a reminder that that is the probability of A intersection B. So that symbol is called intersection. Whereas this one, this U, is called union. Now, that's great, but what does that mean? You can think of intersection as meaning and. What's the probability of A and B happening? What's the probability of them both? Okay, both together. They both have to happen. Union you can think of as an and or. Okay, what's the probability of A happening and or B happening? Or another way to say that is what's the probability of A happening, B happening, or both happening? Okay, so that is the difference in those two. Now, what about this one? Probability of A within the bar B. That is called conditional probability, and we can think of that as given. And so that when we read that, we would read that as what is the probability of A given or assuming that B happened. Okay, so in that scenario, you're assuming that B happened, and then therefore, what's the probability of A? Okay, so looking at these formulas, some of these are very self-explanatory. This one right here, that's just saying that you take the probability of but the probability of A happening is the number of times A occurs out of the total sample space, which is the universal set. Okay. Complementary events basically says the probability of something happening and the probability of something not happening should total 1. Okay. So those are the only options. Either that thing happens or it doesn't. Okay. So complementary, that's useful because basically if we know the probability of something happening and we really want to know the probability of it not happening, we can just subtract 1 minus the probability of it happening to get the chances of it not occurring. Now, the combined events formula. This one is one of your most useful. They're all useful, but this one you can always use. Okay? In any situation. Doesn't matter the situation. The other three have these kind of conditions, okay, that they have to be present in order to use these. So you can only use this formula right here if the two events are mutually exclusive. Okay? The definition of mutually exclusive is that two things can't happen at the same time. Okay? So mutually exclusive, two things that aren't going to happen at the same time. An example of that is if I asked you, what is the probability of pulling a red card or a spade? Okay, well, you could use this mutually exclusive formula because there's no chance that I'm going to pull a red card that is a spade. None of the spades are red. Okay, so notice that this mutually exclusive formula is almost the same as combined events, but you don't have to worry about subtracting away the probability of them both happening. That's because the probability of them both happening is 0. Okay, they're not going to happen at the same time, so you don't have to worry about subtracting that away. Now, your conditional probability we talked about already. That's the probability of a given situation. So they give you part of it. They say this already happened. If we assume that this already happened, what's the probability that this other thing happened? And so you're only going to use that when they're giving you a condition. And then independent events means that the probability of one event happening, let's say the probability of A, it doesn't affect the outcome for B. Okay, so here's an example. Flipping a coin multiple times in a row, those are independent events. Whatever I flipped the first time, great, it happened. I'm going to flip it again. And just because I landed heads the first time doesn't mean anything for my second time. My second time is still 50-50, heads or tails. So each time I flip that coin, it's an independent event. Same thing if I pick a card out of a deck, look at it and then put it back and shuffle. Well, my probability of pulling a red is the same every time. Okay, whatever happened the first time doesn't affect what happened the second time. So I can only use this formula right here when events are independent. So this says that the probability of A and B both happening is the probability of A times the probability of B. Okay, so now that we've talked about what these formulas mean and what the notation means, let's go ahead and look at some problems. Okay, so one of the best ways that we're going to solve problems is using tree diagrams. In math studies, they pretty much always give you like a shell of a tree diagram like we have here. In SL, sometimes they're going to expect you to think of drawing a tree diagram all on your own. So you have to be prepared to come up with that as a strategy. So this says a bag contains 4 apples and 6 bananas. Okay, and they're labeling A as apples, B as bananas. A fruit is taken from the bag and eaten. Then a second fruit is taken and eaten. Okay, so this represents our first fruit that we pull, this layer, and this layer here represents the second fruit. Okay, complete the tree diagram below by writing the probabilities. So this first slot for A is the probability of pulling an apple on the first try. Okay, so that would be 4 apples out of only 10 pieces of fruit. And the probability of pulling a banana is 6 bananas out of 10 pieces of fruit. One of the properties of our tree diagrams, if you'll remember, is that each of our branches that connect to one node should always total 1. Okay? Okay, then we move on to our second fruit. Okay, so this is conditional probability in a way, because think about the fact that if we move on to the second tier, we are going to assume that the part before it happened. So we're going to assume that we pulled an apple first. What's my next chance of pulling an apple? Well, now there's only 9 fruit total, and only 3 of them are apples. So my probability of pulling an apple is 3/9. And my probability of pulling a banana, well, there's only 9 fruit, okay, for the second time. And all 6 of them are still there. Notice they add up to 1, so I know I did it right. Then we look at the other section of our tree diagram, and this time we're going to assume we pulled a banana. Well, if we pulled a banana, all 4 apples are still in there, but there's only 9 total fruits. And then we look at what's the chance of pulling a second banana. If we pull the banana for the first time, well, then we only have 5 bananas and 9 total fruits. Okay, so then it says, find the probability that one of each type of fruit was eaten. This is where we're going to go ahead and multiply down the stems and to get our leaves. So looking at this, what is the probability that one of each type of fruit was eaten? So that's either an apple, then a banana, or that's a banana and then an apple. So we are going to go ahead and find both of these leaves by multiplying across. Okay, so 4 times 6 is 24. 10 times 9 is 90. 6 times 4 is 24. 10 times 9 is 90. Okay. So those are our two probabilities for pulling either an apple then a banana or a banana then an apple. Well, total, what's the probability that one of those two things happens? Well, we can just add them up together. 24 out of 90 plus 24 out of 90, and that gives us 48 out of 90. And it's okay if you do reduce. It's good if you do reduce, but IB doesn't expect you to with probability problems, so you don't have to worry about it. Okay, so let's go ahead and look at a second type of problem. This one says, in any given season, a soccer team plays 65% of their games at home. When the team plays at home, they win 83% of their games, and when they play away from home, they win only 26% of their games. The team plays one game, find the probability that the team wins. Okay, so this is a perfect example of a problem that we need to use a tree diagram for, but they're not telling us to do that. We have to think of that on our own. So, what's the first thing that happens? Well, the first thing that happens is we're either home or we're not at home. So I'm just going to say away. Okay? When we're at home, it says that in order to be at home, it's a 65% chance because 65% of the games are at home. So that leaves a 35% chance that we're away. Now, once we've decided we're playing at home, there's two options. We can win or we can lose. If we play at home, there's an 83% chance we win. So that means that there is a 0.17 chance we lose. Once we decide we're going to play away, same situation, we have the option of winning or losing. But when we play away, there's only a 0.26 chance of winning, which gives us a 0.74 chance of losing. Now, once I've drawn that tree diagram, my whole life's going to be a lot easier because it asks me to find the probability that the team wins the game. Well, there's two ways the team could win the game. Either they're at home and they win, so that's one leaf we have to find, or we're away and we win, that's the other. So I'm going to multiply down the row, so 0.65 times 0.83, that's my probability of being home and winning. Or, so now I'm going to add that to the chances of being away and winning, 0.35 times 0.26. And that's actually the best way to show our work with these kinds of problems to make sure that we get the most amount of method points if for some reason we make a silly mistake. And let's see, that gives us 54. Well, I definitely did something wrong. Let's try that again. I knew that because is a probability ever more than 1? No. So let's take that again. Okay, that's better. I got 0.6305. And with probability, I always recommend that you can leave it exact or put it as a fraction, 1261 over 2,000. It may seem silly, but if you write it as a fraction, you don't have to worry about rounding to 3 sig figs wrong. Okay, then it says, if the team does not win the game, so if they lose, find the probability that the game was played at home. So I am trying to find a conditional probability. How do I know? Well, they're giving me a condition. The condition is the team does not win. Okay, so the condition is that they lose. So the condition goes after the bar. Okay, the probability that they lose. Then it says, find the probability that the game was played at home. The best thing you can do with conditional probability is replace the formula with letters that are meaningful to you. Okay, so my formula from the formula sheet says this. Sorry, I'm running out of space there. Okay, but like I said, the best thing we can do is replace that with letters that are meaningful. Now, I'm going to go ahead and use these letters right here. Okay, so everywhere I see a B, I'm going to replace it with an H. Okay, so that's an H. And every time I see an A, I'm going to replace it with an L. Okay, so this is what I'm trying to solve for, so I'm going to go ahead and plug everything else in. What's the probability, this part says, what's the probability that they lose and they're at home? Okay, so that's me multiplying down this path right here, 0.65 times 0.17. So the probability that they lose and they're at home is 0.1105. And what's the probability that they lose? Okay, well I have two options here. I can go down these paths and add them up, or I already know the probability that they win, so I may as well just do 1 minus that. So the probability that they lose is 0.3695. Now, I am trying to find the probability that they played at home given that they lost. So the only way to solve for that is to divide. So 0.1105 divided by 0.3695, and that gives my final answer of 0.299. Or if I wanted to write my answer as a fraction, 221 out of 739. So if they lost, their chance of playing at home was a 0.299 chance. Okay, let's go ahead and look at this example. It says, in a class of 100 boys, 55 play football and 75 play rugby. Each boy must play at least one sport from football and rugby. So this is a great example of a problem that a Venn diagram would be useful for. So football and rugby. Now we're always going to draw that box that represents the universal set, okay? Because sometimes there's going to be things that aren't in the Venn diagram. They're not people that didn't play football or rugby, but, exist. However, in this case, it says that every boy must play at least one sport. So there's going to be no one outside of those two circles. It says, find the number of boys who play both sports. Well, if 55 play football and 75 play rugby, that would add up to a total of 130. But it says that there's only 100 boys, so that means that 30 of them must have been double counted. So 30 of them played both. Now, if 55 play football, that leaves 25 that play only football. And if 75 play rugby, that leaves 45 that play only rugby. So it says, find the number of boys who play both sports. Well, we already answered that question. That's 30. 30 play both. Then it says, write down the number of boys who play only rugby. Okay? Well, we just figured that out to be 45. Now, let's go ahead and I'm going to put this back here. Football, rugby, we had 25, 30, and 45. And that gave us our total of 100 boys. So it says one boy is selected at random. Find the probability that he plays only one sport. Well, which are the ones that play only one sport? The 25 that play football and the 45 that play rugby. So that is a total of 70 that play only one sport out of 100. So the probability that they play only one sport is 70 out of 100. Then it says, given that the boy selected plays only one sport, okay, so there's 70 that play only one sport, find the probability that he plays rugby. Well, out of the 70 that play only one sport, 45 of those play rugby. Now, could I have used that conditional probability formula? Absolutely. But sometimes it's easy to just reason it out, okay? Take the given part as your denominator and then figure out of those people how many, in this example, play rugby. Okay, so sometimes it's easier to reason it out than use the formula. Okay, then it says, let A be the event that a boy plays football and B be the event that a boy plays rugby. Explain why A and B are not mutually exclusive. Well, we know that mutually exclusive means that they can't happen at the same time. But we know that there are 30 students that play both. So A and B, the probability of A and B happening is not 0. Okay? Definition of mutually exclusive is that they can't happen at the same time, making the probability of them both happening 0. Okay, then it says show that the probability of A and B are not independent. Okay, so we want to find out whether or not they're independent. This is our formula for the independence. So it says that the probability of A and B, so the probability that they play football and play rugby, would be the probability that they play football, which would be 55 out of 100, times the probability that they play rugby, which would be 75 out of 100. Now, if they're independent, what should we get? Well, if they're independent, we should get the probability that someone plays both, which we already know the probability that someone plays both is 30 out of 100, because that's from this middle section right here. That's the kids that play both. So if we check our answer and we say 55 out of 100 times 75 out of 100, and I get a fraction, I get 33 out of 80. If they were independent, I should get the same thing here as I get here. But since I get different things, they are not independent. Okay? Okay, now let's look at an example where they don't give you a context for your situation at all, and they just want you to be able to use the formulas. So it tells us the probability of A is 2/5, the probability of B complement is 1/4, and the probability of A union B is 7/8. So the first thing it asks us for is the probability of B. Now, just a reminder, this B prime, that means the complement of B, or the probability of not B. Okay? So if the probability of B not happening is 1/4, then the probability of B happening is 3/4, right? All we do is 1 minus the 1/4. Now, then it says, find the probability of A intersect B. So we have to think about the formulas we know and think about which one's the most appropriate. The conditional probability one isn't appropriate because they didn't give us any conditions or any givens, any things to be assumed. The independent events one might be useful, except they didn't tell us that it's independent, so we can't use it unless we know that these events are independent. Okay, so we can't use that. So it's looking like the best formula is the combined events formula. Okay, and that says the probability of A union B equals the probability of A plus the probability of B minus the probability of both. So we have to fill in what we know. We know the probability of A union B is 7/8. We know the probability of A is 2/5. We know the probability of B is 3/4. And we're trying to solve for the probability of A intersect B, so I'm just going to call that X. So all we have to do is solve this problem. And so we get X is 11 out of 40. I trust that you guys are able to do the algebra solving that problem. Okay, so the combined events formula worked great. The part C says find the probability of A given B. Okay, when we're doing that, that's a conditional probability formula. How do I know? Because they give us a condition, right? The condition is B. So I am going to go ahead and write out our conditional probability formula. Probability of A and B equals the probability of A times the probability of B given A. Now, notice that what has happened, we're trying to solve for the probability of A given B. And our formula is the probability of B given A. So we have to switch everything. Switch all the A's and B's before we can use this formula. Okay? Now that we've switched all these, we're going to plug in what we know. We know the probability of A and B, or that would be the same as the probability of B and A, right? the probability of A and B both happening would be the same as B and A both happening. So that would be 11/40ths, excuse me. We know the probability of B is 3/4. And then the probability of A given B, that's X. That's what we're trying to find. So all we're going to do is take our 11/40ths and divide by our 3/4. And that gives us that the probability of A given B is 11/30ths. Okay, one last problem. This one is similar. It asks us to basically do this whole problem without any context, just using the formulas. So it tells us the probability of E is 2/3, and the probability of E and F, or E intersect F, is 1/3. Calculate the probability of F. Now, something key here. It tells us that they're independent. So that means that we can definitely use this formula, the independent events formula from your formula sheet. Okay, so let's see if there's anything useful to plug in. The probability of E is 2/3. We're trying to find the probability of F, so we don't know that. And the probability of both is 1/3. So all I do is take my 1/3, divide by 2/3, or multiply by 3/2, right? The reciprocal. And so my 3's cancel, and I get my probability of F is 1/2. Okay, then it asks for the probability of E union F. I got to look at my formula sheet and decide what formula is going to be the most helpful here. Well, we already used the independent events formula, and that one doesn't have the union on there. Okay, our mutually exclusive formula has the union, and so does our combined events. However, we know this is not mutually exclusive because the probability of E and F is not 0, it's 1/3. So we can't use mutually exclusive, so we're going to use our combined events. And so all I do is write out my formula. And plug in what I know. Okay, probability of E we know is 2/3. Probability of F we know is 1/2. Probability of both we know is 1/3. And so all we have to do is combine those. And for sake of time, I'm going to go ahead and take care of that. So that gives us 5/6. And that's our probability of E and or F. Hopefully that gives you a good idea of a couple different kinds of probability problems. It's really tough to be able to, it was really hard for me to pick a sample of problems. It's kind of impossible to pick a perfect representative sample. So I tried to pick what's most common. It's most common to see tree diagrams and then to see formulas and Venn diagrams. Those are your most common. But other things you might want to look at in the book are your dot diagrams that help you come up with the sample space for two things. You also might just look at other problems because there are so many different kinds of ways that they can ask you these problems and that they can phrase these questions that practice makes perfect. So let me know if you want some extra practice problems.